We are continuing our discussion of solving radical equations, and these are going to be for equations that are a bit more involved. So what will be essential to us is making sure that we're really concentrating on step 2, which is to raise each side of the equation to a power equal to the index or root of the radical. And we're going to continue also making sure that we're checking our potential solutions for extraneous roots. Now, a part of this lesson is going to be needing the process of factoring. And factoring is the reverse process of distributing. So distributing, we're looking at multiplication. Therefore, factoring is kind of utilizing the concept of division. So the first step in factoring is always to factor out the greatest common factor, also known as the GCF. And for a polynomial, the GCF is the expression of the highest degree that divides evenly into each term of the polynomial. Now, we've used the phrase polynomial twice here. So a polynomial in the variable x is a finite sum of terms of the form a times x to the n power. So recognizing that we have our variable x in the numerator, not in the denominator. So we have no fractions. So to factor a polynomial of 4 terms, we can also try factoring by grouping, and we'll see that together today. So we also need to understand what a quadratic equation is. So let a, b, and c represent real numbers, but a cannot be 0. So a quadratic equation in the variable x is an equation of the form a times x squared plus b times x plus c, and this is set equal to 0. Now, it is okay for b to be 0, it is okay for c to be 0, but a cannot be 0, because if a was 0, then that would eliminate the term with the power of 2, and therefore it would not be quadratic. A quadratic equation always has 2 solutions, and that follows from the fact that the power of this equation or degree is 2, therefore it will have 2 solutions. And the solutions may be real or they could be imaginary. To solve a quadratic equation, we can use the zero product property, which states that if we have 2 things that multiply to be 0, then one of them has to be equal to 0. So we'll see that in action today. So for example number 1, we're going to go back to the first step for solving a radical equation, and recognize that the radical is not alone. And so we need to get this alone by adding x. So the square root of x plus 11, we need to add x to the right-hand side, so this is equal to x plus 5. And now we're going to focus on the second step, which is to square, because the root is 2, both sides. Now this is the entire right-hand side. So it doesn't say to square everything, it says square each side. So that means we're going to take x plus 5 and we're going to raise it to the second power. Now for the left-hand side, this simplifies to be x plus 11 because the root and the base cancel. But the right-hand side, we need to remember what this square means. So x plus 5 quantity squared means x plus 5 times itself, and we need to distribute. So left-hand side, we'll leave it alone as x plus 11. But the right-hand side, when we distribute and simplify, we have x squared. The outside distribution gives us plus 5x, but the inside distribution gives us plus 5x as well, for a total of 10x. And then the last distribution gives us 25. Now this is a quadratic equation because the highest exponential power is 2. Therefore, we need to set this equal to 0 in order to solve it. So we only have x squared. We leave this alone. We have an x on the left side, so we need to subtract that to combine it with the right-hand side for a total of 9x. And then we have an 11 on the left side, so we need to subtract that to combine it with the 25 for a total of 14. So if we look at what we have for our A, B, and C, notice A, which is the coefficient of our squared term, is 1. B, which is the coefficient of our x term, is 9. And then C, our constant, is 14. And because A is 1, we can use the algorithm. What are factors of C that add to be B? So factors of 14 are 1 and 14, but that adds to be 15. But factors of 14 also include 2 and 7. And 2 and 7 does add to be 9. So that means that this factors into the product of two binomials, x plus 2 and x plus 7. Take a few moments and recognize. If we were to redistribute this, this gives us x squared plus 7x plus 2x. That does give us our 9x and plus 14. Now using our zero product property, we're going to set each factor equal to 0. So x plus 2 equals 0 or x plus 7 equals 0, which means x equals negative 2 or x equals negative 7, but we need to check this. So always go back to the original. Our first check with negative 2, we have the square root of negative 2 plus 11 minus negative 2 is supposed to equal 5. The square root of 9 plus 2 is supposed to equal 9. And this solution does check. Okay, so negative 2 is a solution. For our second check, we're checking with x equals negative 7. So we have the square root of negative 7 plus 11 minus negative 7 equals 5. This gives us the square root of 4 plus 7 is supposed to equal 5. And we have a problem here, don't we? 9 does not equal 5, so this is what we call an extraneous root. This is not a solution. So negative 2 is our only solution. Your question is to solve the square root of d plus 18 plus 2 equals d. Our next example, notice that we have two radicals and we also have a constant of 3. So when you are told to isolate a radical, one radical is isolated. The other radical is not isolated because of the 3. But if I were to isolate the radical on the right-hand side, it would unisolate the radical on the left-hand side. So this is as isolated as our radicals can get for now. So we're going to recognize I need to, at this point, square both sides. So this is the square root of 2 minus y squared equals 3 minus the square root of y plus 3 squared. So the square root of 2 minus y squared is 2 minus y. And then we need to expand this by recognizing that the power of 2 means that our base is a factor in multiplication twice. So 2 minus y remains, and now we're going to distribute. 3 times 3 gives us 9, minus 3 times the square root of y plus 3, minus 3 times the square root of y plus 3. And then notice we have minus the square root of y plus 3 times itself, so that will give us plus. And the square root of y plus 3 times the square root of y plus 3 will give us y plus 3. Combining, we have 9 combined with 3, which gives us 12. Notice these are exactly the same. So there's 2 of them. So twice 3 is 6. They're both negative. That remains. And then we also have this plus y. We have made progress here in the fact that now we only have one radical. So we're going to isolate our radical. Because this is negative, I'm going to choose to bring it to the left-hand side by adding. So this becomes 6 times the square root of y plus 3. Notice we're going to subtract this 2, which gives us 10. And we're going to add this y, which gives us 2y. Now there's another thing that we can do here to make our life easier, and that is to notice that we have a 6, a 10, and a 2, all of which have a factor of 2. So I'm going to divide everything by 2. So we're going to divide this by 2, this by 2, and this by 2, giving us 3 times the square root of y plus 3 equals 5 plus y, also known as y plus 5. And now we're ready to square each side. Now this is part of my base for that power of 2. So 3 is being squared and giving us 9. And the square root of y plus 3 is also being squared, giving us y plus 3. But that is being multiplied by our 9. Y plus 5, and I forgot to write my power of 2 there, pardon me. Remember, we need to square both sides. Gives us y plus 5 times y plus 5. Next line, we have 9y plus 27 when we distribute that 9. And then distributing y plus 5 to itself, we have y squared plus 10y plus 25. And notice this is quadratic. So we're going to set this equal to 0. Y squared. We're going to subtract 9y, leaving us with positive y. We're going to subtract 27 from 25, leaving us with minus 2. And again, in this sense, A is 1, B is also 1, and C is negative 2. And because A is 1, we can use the algorithm, what are factors of C that add to be B. So y squared is y times y. And factors of 2 are only 1 and 2. And because this is a plus y in the center, we want the one with the larger absolute value to be the positive. So this is plus 2, but minus 1. And if we are to redistribute, that does indeed give us the plus y for the center. Using the zero product property, y plus 2 equals 0 when y equals negative 2, or y minus 1 equals 0 when y equals 1. And I'm going to leave it to you to check both and see if one or both of them are true solutions.